And now, because this is why you came, I'd like to introduce David Strauss, who is one of Rackspace's largest customers at Pantheon. They have, you said, over 1 million containers running right now. So I think I'm ready to listen to how that happens. You guys? All right, thanks for coming out, David.
So I'm here to talk about containers, particularly versus virtual machines, because I think the case for virtual machines has been made extremely well, if not by just the efficiency of being able to work with them, than by the sheer size of EC2 and Rackspace's product in terms of the uptake in people deploying applications. But I'd like to, mostly I'm trying to move beyond virtual machines in terms of why we should care about the efficiency of that, how it affects us as developers, how it affects us as sysadmins. So a touch about, a bit about me. I have a long history going back to the Drupal project on the infrastructure team, the security team, working on performance and scalability solutions for that, which I've parlayed into my work at Pantheon, which is my current company, where I'm CTO and co-founder, and we run millions of containers to support our Drupal and WordPress infrastructure for our customers. I'm also a committer on the Systemd project, which is a layer that is very commonly used in container implementations for things like CoreOS and Red Hat SecureD, which is a kind of emerging product that they're doing on RHEL 7. And with some thanks to Nick Steelau's presentation on Mo servers, Mo problems at DrupalCon. I've cribbed some slides from there to enhance this after finding out that you folks have seen more than a handful of container presentations, and I wanted to make sure you get something good and new and abundant. Nick is our Director of Operations at Pantheon. So, first of all, the goals of computing. First of all, you got to make it work. But second, after that, almost immediately following, you got to make it efficient. And there's that's through running efficiency in terms of running the software, it's efficiency in terms of developer time, and there's really no number 3, I think, to computing. Like, once you get it working and you work efficiently and you get running efficiently, that is the goal of software. And when it comes to the runtime environment of software, whether it's bare metal servers, virtual machines, or containers, that directly affects every single part of the second tier of this in terms of how developers relate to the systems and how much we can pack into our computational infrastructure. But I want to take a step back and kind of look macro scale at the impact of our industry on the world and how we relate to that impact. Data centers take, as of 2012, it's probably a lot worse now. Data centers took 2% of the US power grid. Worse is that we're not using that very well. There was someone who did a neat side channel attack basically on a bunch of EC2 instances where they deployed these tiny VMs that would run alongside a lot of other VMs on these boxes, and they deployed them wide scale, left them running for a while in EC2, and then you can read certain attributes from processors and find out how busy those processors are, even if they're not running your workload. And he determined that on average, EC2 instances were about 7.3% occupied, at least in terms of CPU load. And you can see kind of the spikes in terms of the usage where it's spiking obviously on Monday, beginning of week, off much lower load on weekends, but overall, not that efficient, especially when we're talking about the scale of how much power this is actually using of the grid. And when it comes to making computation much more efficient, it's always kind of come down to some sort of time sharing. And that has a long history in computation, and it goes all the way back to when we started building machines with batch processing, terminals and virtual machines, clients and servers, thin GUIs, clients like Sun Rays connecting up to servers, web clients connecting to servers, web and mobile clients connecting to cloud virtual machines. And that all ultimately is designed to pack the needs of many people onto a certain amount of infrastructure. And the current way that people are doing that for the majority of their systems that are getting deployed on infrastructure that's kind of on demand is happening through virtual machines. And I want to, before I can kind of go into why I think containers are a superior alternative, I want to outline why people love virtual machines, because there are a lot of really good reasons why people use virtual machines. First of all, consolidation. Like, there's no other way that you can basically have these kind of virtual computers where you're able to take something that might have taken up a rack worth of hardware, and if they don't really need full machines, be able to compact them into these virtual machines that then get consolidated onto a single system. And that's related to, and that's possible because they provide something that's very familiar to developers and system administrators, which is something that looks kind of like a regular machine, even though it's not a real machine. And that's referred to, at least in the design world, as skeuomorphism, the idea of taking a form that people are familiar with and then taking it into a realm where it's not technically required, but is something that is familiar to people for using it and developing against it. And I've never really heard people refer to virtual machines as skeuomorphs, but they really are, because when you have an operating system and something that looks like virtualized hardware, and a virtualized network card, a virtualized audio card, a virtualized mouse, a virtualized keyboard, you're programming against something that is not really the reality, but is designed to be intentionally familiar by repurposing old designs. And the advantage of skeuomorphs and why virtual machines have been able to use them so effectively is that, to kind of cut down this a little bit on the quote, skeuomorphs are stories of utility frozen in time. They work because they leverage a user's past experience and apply that understanding to something new. And working with virtual machines is not really something that requires a major change in the skill sets that we have to work with them, but we're still able to take advantage of that new infrastructure. And it's almost inevitable that this kind of stuff has to happen with the slicing, because we have these big machines now that people are buying that are far larger than most applications actually need. The most economical machine to buy, say on like a physical rack at Rackspace, is at least 128 gigabytes of RAM, possibly 256 gigabytes of RAM, and most people just don't need that. And so we've needed to slice up those resources, and historically virtual machines have been one of the only major ways of doing that with reasonable efficiency and compatibility. And it provides this kind of portable unit that can move around, you can fail over between instances, you can get availability with it, you get this kind of consistent hypervisor where you can forklift a virtual machine off one thing and put it onto a different physical server, and you get these kind of consistent images that have allowed all of the proliferation of things like AMIs on Amazon's cloud, where it's consistent. It's virtualized hardware, but at least it's consistent from machine to machine, and it isolates users from having to deal with the intricacies and idiosyncrasies of real hardware on the systems. And it's also about automation, that it's so much better to be able to program against an API for working with these machines and deploying infrastructure for things. Like, it's really no fun to set up a contract and have to wait weeks or a month to actually provision servers. And one of the best things about that the cloud has offered is this kind of on-demand and off-demand infrastructure where when you need it, it's there. When you don't, it can go away. And they've also gotten really efficient, too, with a lot of the hardware optimizations that have happened. In terms of the workload that virtual machines run, they're maybe around 99% efficient in terms of CPU at running the operating system and the application. And they've reached a high degree of maturity. And they weren't always this way. As of the 90s, they were far, far worse than this, and you wouldn't ever compare it to bare metal hardware. But we see people today where they'll have a bare metal machine, and they'll actually have a hypervisor and a single guest on that machine, because the virtualization layer is so efficient that there's not even that much to worry about the idea of passing it through that extra layer, even if they could to install the software directly to the physical machine. But I think containers are the next step in many of these areas. and they further reify the advantages that virtual machines have been offering us. And to kind of misinterpret an advertisement from VMware, you know what virtualization did for computing, why stop there? And of course, they're referring to their kind of software-defined networking stuff, but my question is, why stop at virtualization when we found a kind of mechanism and reasons behind that mechanism that have allowed us to be so much more efficient as developers and system administrators? Looking at the kind of value that things have offered in terms of when you can kind of standardize that unit, whether it's virtual machines or containers. This was such an interesting chart that inspired a lot of the folks who worked on Docker, and it inspired a lot of the branding behind Docker of the idea of a container ship, because there was an order of magnitude change in the efficiency of an entirely different industry when they kind of changed the way that they worked with the units that they would move around and deploy to be something that would be completely standardized. And that's, virtual machines do that to a large degree. I think containers can do that to an even greater degree in terms of circumscribing the boundaries of an application and the needs of some sort of deployable service. And I went over the other history, but it was brief because I omitted everything about containers that kind of happened along the same period of time. Containers actually go back quite a long way. The first reference I could ever find to something that looked like containers was AIX 6.1, which is IBM's mainframe Unix, with what are called workload partitions, which allow you to run separate things on the mainframe server and then allocate some fraction of resources to one workload and some fraction of resources to another without having to fully virtualize and without having only one run at a time. On one of the first comments that I got on my Linux journal piece on containers being the future of the cloud was from Paul Henningkamp, who has done tons of FreeBSD work, and he was like, why doesn't anyone ever talk about this? So I'll throw it into this presentation, because FreeBSD did it first, for the record. Nobody cares, but FreeBSD did it first with jails back in 2000. And Solaris did it kind of on quick following with zones, also in a way that I think only a handful of people are really caring about now. But then the Linux world started to take note of these kind of capabilities. And the interesting thing that happened here is that prior to this time around 2007, when Google started working with C groups in the kernel, the only way that you could get reliable partitioning of system resources on Linux systems was through virtualization. If you wanted to give some percentage of CPU to something and some percentage to something else, you had to basically just set up VMs and then run it in there. And there are other more traditional resource distribution things that Linux systems have had that harken back to Unix, things like nice and IO nice. But the problem with them and the distinction versus what's going on now is they were winner-take-all technologies where the thing that was least nice would get as much CPU as it could eat, and then whatever the scraps were from the thing that had nice minus 20, nice minus 19 would have a shot at, and so far down there. Which means that if you were less nice on the system, you could get starved of resources, and the things that were less nice could starve other things of resources. And with these technologies here, that's not the case. These are not starvation-based technologies. They're based on the idea of shares that go out to different systems, where if you have abundant resources, then it's burstable. Everyone can kind of get all they can eat, but as soon as there's contention, what happens is it distributes them according to the shares that are distributed to any individual application. And I'll go into some kind of demo slides of that soon. Near and dear to me, Systemd launched in 2010, which is replacing the layer that is starting right after the kernel, and is the first time that configuring C groups and namespaces is shipping as part of an OS, and something that is starting by default and as something that allows configuration of those attributes with any service on the system. So that has a lot of overlap with the container concerns, because there's no concept of containers in the Linux kernel. The Linux kernel only has namespaces, C groups, seccomp filters, and a number of other security isolation mechanisms, all of which, when used harmoniously, can result in something that looks like a container. And so it doesn't matter whether those facilities are invoked by something that calls it containers or doesn't. It's really the same ultimate control going on in the kernel. But it took years before it became much more popularized. In 2013, around, I want to say, May or June, Docker announced its initial kind of alpha availability of its repository. And then later on in 2013, there was work toward CoreOS, which I'll also get into. That's a system that takes together systemd plus Docker plus a minimal base OS and turns it into kind of a container operating system. And in 2014, LXC, which is the primary driver behind Docker for running containers, went 1.0, which means they have an actual stable API they're going to be supporting for, I think, about 6 years or longer. And Red Hat announced GearD, which is somewhat derived from and related to CoreOS, but means that one of the biggest Linux distribution companies out there is adopting containers as a core shippable part of the operating system. GearD configures systemd to launch Docker containers on the OS. So I went over the advantages of virtual machines and why people use those, but I want to go over kind of comparative advantages of containers as they relate to those attributes that people so favor in virtual machines. First of all, I want to kind of cut down on this idea that familiar makes these things good, where it's probably well known to any Apple user in here that Apple dropped all the skeuomorphisms in their iOS release beginning around 7 because they did a lot of introspection in terms of what that was providing in terms of value to their customers, and came to the conclusion that the familiarity of those designs and to traditional physical world objects was eventually getting in the way of further refinement of the interface and the experience of users. And I think that virtual machines have finally hit that phase. And to kind of take the last part of this, I think we're finally at the stage where virtual machines are kind of leading us astray, where the idea of providing this container that is abstracted and looks like a physical machine is now inherently limiting in terms of the way that we're building our services and running our systems. One of the biggest reasons to use containers versus virtual machines is that tiny slices are useful. Back when Rackspace launched its cloud product, you could originally get 256 megabyte virtual machines, and those were retired not that long after they were launched because you really couldn't run an operating system any useful workload on 256 megabytes because the OS itself would be taking more than half of that. And containers can compete with that by only needing the resources for an application, where 256 megabytes is actually a very useful slice, and as I'll go into later, we're generally using containers that are smaller than that at Pantheon. Before I kind of show this idea of a train and the idea of kind of carrying freight from one location to another, or carrying passengers from one location to another, and when you look at the efficiency of virtual machines, I said that they were 99% efficient in terms of running the operating system and the application. But the caveat to that is that they're very efficient at an inefficient workload. In the same way that planes and trains can be very efficient at transporting people, but they're not very efficient when you compare them to a completely different category of like people getting together on a video conferencing channel. And I kind of think of containers the same way because containers are probably about as efficient as virtual machines at running the workload you give them, but the workload that they're required to run is massively smaller because it doesn't include an operating system. And there's some work to use virtualization technologies to provide containerized like services, where I know one of the authors of KVM is working on something where it basically runs just a JVM in the virtual machine, but those haven't come all that far, and they still have a lot of the caveats in terms of being able to do wide-scale management of those systems, because there's still kind of opacity to the virtual machines that are run that way versus containers. One of the big deals for us in terms of how we're able to run so many containers on our infrastructure is that we can pack them really dense because they're light, and we can reorganize them quickly. When people think about plane flights and overbooking, the reason people get really angry about facing overbooking and getting bumped off a flight is because it probably adds hours to their travel time before they're able to be moved to a different flight to be able to make it to their destination. And virtual machines have a similar problem where if you overbook a server and you have too much virtual machine load on the box and you need to migrate one of them away to rebalance your load, the actual time to rebalance a virtual machine is very high because it's carrying a full operating system plus the application binaries and libraries plus the application state data usually. And that means that even a basic, even a database server, which is going to have a lot of application state, is still probably going to have more OS state than application state. And that's like 100% worse than the container case. And if you have something that's really lightweight, like an application server, where maybe you have 50 megabytes of application state, it takes possibly hundreds or thousands of times as much data to migrate that from one machine to another if you're using virtual machines versus containers. And so what that means is we pack them super dense. And we're running our machines at around 80 or 90% of their CPU capacity, because when there is a spike, we're able to move things around very quickly, because containers don't have that much state. And in terms of automation, which is the friend of every developer and DevOps deployer, containers are just faster. If you look at bare metal, even if you have a hotline to your hosting company, it still is going to take them probably a day to get a new server in the rack. And then if you provision a virtual machine using EC2 or even the Rackspace Cloud, it's still going to take on the order of minutes to get those online. But containers take on the order of seconds to get online. And depending on how much state you have to transfer to set up a container and how much configuration you do, you can easily hit below 5 seconds for setting up a container on a lot of these systems. And that just makes deployment a much happier experience, because you get feedback like that. You can scale up that much faster. If you can scale up that much faster, you don't need to maintain as much spare capacity in terms of virtual machines, because virtual machines taking 5 to 10 minutes to provision may be too slow to respond to changes in load of systems. Here's an example. This is one of Nick's things that he likes to do. He likes to set up Debian boxes on Fedora boxes and then launch them with containers. And this is actually booting a Debian user land, and then it starts the init process and drops into a shell, and that's how long it takes in terms of wall clock time to start it up. Now that's not transferring all the state data for the Debian image over to that system, but it makes clear how little overhead there is on the kernel side of actually flipping on all these isolation layers in terms of the isolation for performance, scalability, system resources, and security. So I'll talk a little bit about containers at Pantheon. We keep them really dense. We deploy about 10,000 containers to a box, but we don't run them all at the same time. We use a technology called socket activation, which ships with systemd to be able to launch the containers as requests come in. And that allows PHP, MySQL, etc. to only start the container when it's actually needed. So when the box boots up, all of that happens is the socket listeners start, and then all the processes are actually, or the services are idle. And then as requests start coming into the box, then those things start up. And then when a service has not been active for a while, we do a thing called reaping it, where we actually take it back offline. Now, we still run a pretty good number on these boxes though. So just looking at the active containers on these boxes, we're averaging around anywhere from 50 to 150 for the application servers, and about the same for our database servers. But even in terms of the operational containers, if I'm just slicing among those and ignoring the efficiency gains of having a bunch of idle containers that are able to start up like that, we're still only taking a 205 megabyte memory footprint for each of these containers, which is smaller than the virtual machine size that Rackspace discontinued because it wasn't useful. So it's compared to the smallest VM size that's available, that's less than half the RAM of the smallest VM size available from the Rackspace cloud these days. And in terms of provisioning, we are able to get most of the ones requiring less configuration, and by configuration I mean Chef running in the container, under 20 seconds. These other ones that are kind of up to 30 to 60 seconds, that's just time of Chef running and configuring, not the time for the container to come online. But we're able to deploy additional capacity for our customers in anywhere from 20 to 60 seconds, depending on the kind of flavor of container that someone wants. And then we have an algorithm across our boxes that is called the kind of site experience monitor that runs a representative workload on each of these boxes so that we can look for contention. And then that score gets submitted up to our API to determine where to throw these containers. And this time you're seeing here is the time from the box getting the request to get that container running for a customer to the time that it reports back to the API saying this container is ready for service to run the customer's workload. And I threw a little star thing on here. We have a pilot deployment at Rackspace in Chicago on the managed colo, where we used the DRAC cards to provision the OS directly to the machines, and we're slicing all of the resources using containers, and that's about twice as cost effective as cloud right now. Now, that doesn't include, you can't get the machines on demand, but it's neat because there's no overhead at all in terms of a second OS on the machine or a VM even within, there's not even a single VM on a single hypervisor in those cases. We do all this by using a lot of technologies that I was talking about that basically talk to the kernel with these facilities of C groups and namespaces, and I kind of want to go into those bones of it. And this is basically the stuff that LXC configures, or if you use Docker, Docker tells LXC to configure, or if you use systemd tells the kernel to configure. Containers are basically just the synthesis of C groups and namespaces. And C groups is the Linux kernel facility for managing distribution of resources among different processes and children of those processes on the system. And this is an example where maybe you have production and development on the same box, and you can give, say, 75 CPU shares to the production pool, and you can provide 25 CPU shares to the development. And that's burstable. If the CPU is available, either gets as much as they want, but as soon as things are hitting the wire and resources are tight, your production systems are going to get the bulk of those, although you would still be able to actually deploy using your development resources because they wouldn't get starved. And this was his other example of processes for people I like and processes for people I don't like. This would be great if you were a shared hosting provider in terms of like people on like a free plan or paying you $1 a month. You could put them in this bucket where maybe they get almost nothing when resources are under contention, which is all the time on shared hosting providers. And there's a whole bunch of these. There's the memory controller, which is able to cap the amount of memory that it's either able to provide a hard limit on things in the C group, or it's able to provide a limit where if it goes above that, then it goes into swap, even if the rest of the system's not going into swap, which I'll caution you is usually worse than just giving that process extra memory if you can. That going into swap, even with a few processes, can put a huge amount of load on the system. CPU set is useful for NUMA architectures. All the new servers in the current generation from Dell, if you actually do bare metal, are all NUMA based, which means that they have a CPU or 2 or 3 partitioned, and the memory, half the memory is maybe owned by one side, half the memory by the other, assuming it's kind of one level NUMA, or it could be more levels than that. And that means that there is affinity where if you want to have a process run with its local memory, you want to run it on the side that actually owns the memory related to that process. Otherwise, you pay a hit as it goes over this kind of bridge between the NUMA segments. And the CPU set allows you to bind processes on the system to certain subsets of that. You can also use it to basically slice up a server at the core level, where you could say give one core to this container and 2 cores to this container, where that provides a very hard partition where there's very little contention between what's being set up. CPU ACCT, which does accounting, it checks the actual amount that it's using of the stuff that you've allocated it, so you can basically see how greedy a given process is and whether it's hitting its limits. The CPU controller is what does CPU shares that I was talking about before, where you just give shares to different things, and then when things get under contention, it divvies them up based on how many shares have been allocated to a given thing. I don't know what the devices controller does. Presumably it's about device access. Block I/O is where you can provide block I/O weight to different processes. This is great for database servers because they're often under I/O contention. Block I/O weight works the same way as CPU shares, but it's for block I/O. So if disk access starts getting under contention, you can give something 75% of the available I/O capacity of the system without, so it shares it fairly. And the network class controller, I think that affects what tags things get on the network as their traffic is going in and out, where you can do kind of quality of service things where these certain processes are able to flag their traffic in a certain way, and these other processes get their traffic flagged in a different way, which would be probably very useful if you ran, say, VoIP systems, which we're not doing, so we don't use. The only 2 controllers we use are, well, 3 ones we use are CPU accounting, CPU, and block I/O. And we initially were experimenting with CPU set on the NUMA systems, but eventually found out a better way to do it with the normal schedulers. Let's see here, an example. So let's see, files. Okay, so control groups right now are manifested through this kind of file system, the pseudo file system in the true kind of Unix and Plan 9 tradition of exposing these resources over something that looks like a file system, although that may be going away because there's a push from the systemd community to move all C groups management into a single daemon that runs in user land and brokers the access to it, which would naturally be systemd, which is kind of self-serving. But so I don't know how long this file system is going to be around or how it will manifest itself after that transition, but this is what it is today. So if you created a C group, it creates, because it's not a real file system, it actually creates a bunch of kind of child pseudo files that you can then write to or read from in terms of usage, limits, what processes are actually in the group. You can do something where you limit, you could limit it to 100 bytes of memory in a certain group called AA, to memory.limit in bytes. And then this was basically setting up a CPU group using libc groups, which libc groups is kind of the old school way to auto-classify processes. You can create a rule set with libc group in Etsy based on the executable name or the user or the group to auto-classify what C groups those things live in. It's actually pretty easy to use and slick. I don't know how much longer that utility is going to be around with the work the systemd is doing, but this is kind of an example of doing some of that dynamically from the shell rather than through the configuration file. And this gives 100 shares to AA. The interesting thing about shares is the only value they have is relative to each other. If you give only one thing on the system shares, it won't really affect anything. If you give 2 things shares, it doesn't matter whether you give this one 100 and this thing 200, or you give this thing 1 and this thing 2. It's just the ratio of the shares as they kind of come together to form a pie of how the system splits the resources. And this is one where if you set this kind of teensy memory limit group into 100 bytes and you impose it on yourself, your current PID, and you try to do anything, even a basic bash command, it's going to kill itself immediately because you're going to run out of 100 bytes of memory like that. CPU shares is my favorite though, because I think it's at parity with block I/O weight, but it's easier to demo the CPU shares. Where if you have if you execute this kind of one CPU-hungry process in AA and this one other CPU-hungry process in BB, and one has 100 shares and the other has 10, you'll see that one is getting approximately 10 times the amount of actual CPU of the other one. The other counterpart to this stuff is namespaces, where C groups are designed for limits on resources and distribution of resources. Namespaces are based on access to resources and isolation of things like file system mounts, inter-process control. The user namespace is new and very interesting because with containers, it should be competitive with mandatory access control systems like SE Linux eventually, because the idea is that you can run the container in a user namespace, and even if someone supposedly gets root in that container through whatever exploit that allows them to set some value to, say in the kernel, that they can escalate to being that UID, it still would not actually be root on the base system, because everything in that container would be namespaced into a single PID on the base, or not PID, a single UID on the base system. And the same thing exists for some of the, well, for PID resources, there's kind of a mapping where everything has like a base system PID, but the container itself, the first process it starts can be PID 1 as far as the container sees. And the same thing for network. You can isolate a container and just say, here's your kind of virtual localhost interface that is only visible to things in that container, and then you can wire it up to whatever interfaces you want, whatever kind of IP cables rules you want. The way that Docker uses it is it'll create a container, it'll use IP cables to forward one port into it for whatever service, or well, can do more than one, but some ports into that container, and then outbound access, at least IPv4, is done over NAT. And then that way, none of the containers can see what each other are doing, but they can still have outbound access, and they can still run the services they're supposed to run. And this is neat because these things have gotten added progressively over the past 5 to 10 years to the kernel, and user namespaces are so new that they're not even being turned on in most distributions yet. So we're still kind of on the crux of this really getting realized as great technology that can isolate competitively with VMs. Unshare is the Linux kernel syscall to be able to basically say, I'm going to create a new namespace now, and anything that I create from that point in my own namespace will not affect the other party, and vice versa. And that can be used to unshare any of these other namespaces that I mentioned. This is just an example of unshare net bin bash. And then I believe in that bash shell, if you did a like an ifconfig, I think you would only see a localhost interface, and that localhost would still not even be the same thing as the localhost on the base system. It would be kind of a bare, fresh localhost that could be used by anything in that kind of pseudo container. And then nobody actually likes to work with any of those tools directly. They're all kind of crufty, and they don't really combine very well in the sense that namespaces are configured completely separately from any of the C group stuff, and the rules systems for each of those are kind of scattered. So a bunch of people have kind of collected those together and called it containers and allow you to configure them all together. One of the originals is liblxc. I believe IBM created this project, but it has a lot of modern bindings for things like Python 3, Lua, Ruby, Go. It's pretty much the industry standard if you, of tools that are library-based that don't involve running any kind of daemon on the system. And a lot of other things wrap liblxc that are kind of container frameworks. It's the default driver for Docker. Google, as soon as they found out about the container craze, kind of hastily released let me contain that for you, basically to kind of prove to the world of, hey, we've been doing this forever inside Google, even though you haven't seen it because we don't talk about any of these internal projects. Here is like this thing on a platter. I don't think it's actually very useful to the outside community, but it's kind of fun to poke around because Google actually runs everything in there. The caveat to this one is that it's designed to combine things together in containers that are kind of mutually friendly. Like they assume that it's not designed to do much security isolation, and it's not designed to handle cases where someone is trying to actually circumvent the resource isolation that the containers are providing. So this is not something that I would use for mutually hostile containers. It's more that you want to run 5 things on a box and have them be balanced in terms of the resources they get.
What's the relationship into the mainline kernel? Is it included?
All these namespaces and C groups.
Let me contain that for you. It's on.
This is userland.
Okay, it's userland.
It's userland and it invokes kernel facilities. Okay. All the namespace and C group stuff is in the mainline kernel. And so you don't have to run these, with the exception of the user namespaces, which are disabled in most distros, but none of these require user namespaces. You can use all of these tools with a completely vanilla kernel. Whoops. And there's systemd inspawn, which is systemd's little kind of, it started as a toy, but it's not really a toy anymore. And it provides a pretty good set of tools for setting up the same kind of isolations for these various namespaces and C groups. It's probably one of the lightest weight because I think you can do all the configuration options for it just on the command line, and you can see all of them from the man page, and then you can just have it basically run a process with whatever set of isolations you're specifying. And of course, because all these distros are shipping systemd, this will actually be probably the most broadly deployed containerization tool because it's just bundled with systemd. And then inspawn can actually launch, I don't even know how to pronounce this combination of like OS 10 virtualizing, the logo is meant to represent OS 10 virtualizing a Fedora machine that is then launching a Debian userland inside a container. And that actually runs pretty efficiently. Not that it's very useful, but here's kind of how you would do it. Deb Bootstrap is actually available on Fedora to create a Debian userland, or Debian, I think it is just a userland, in whatever directory you want, and then you can use inspawn to start it, and then you're basically in a Debian shell. And you can actually run aptitude and install packages and all kinds of fun stuff. And then Docker kind of is providing yet another layer on top of this where all these other utilities are designed to organize the kernel configuration for things like C groups and namespaces, but none of them really specify what goes into the container and how containers communicate with each other. And Docker really kind of solved that problem on top of it, where Docker configures everything below it, but also allows a definition format for kind of container images, which is what I was getting into before about why virtual machines are so popular, because one of the things is that people could create AMIs and anyone could use those AMIs in the cloud, and anyone could create virtual appliance images that could then run on things like VMware. And Docker is actually bringing that into the container space where there's a simple, straightforward way to kind of publish container images for consumption by anyone who's running this kind of infrastructure on their boxes. And then there's kind of a spectrum here from the highest level down to the lowest level, where and also kind of capability as well, where let me contain that for you is definitely like the most basic and lightweight kind of thing, all the way up to Docker, which is, even comes with its own infrastructure for distributing images. And then CoreOS kind of saw Docker and was like, that's great that you can run this thing where you can run container images in a unified way on these things, but all of this OS that's underneath Docker is just so excessive when you've got Docker. And so the CoreOS idea is that they took from Chromium OS, which is what Google uses for Chromebook computers, and the thing they took from that is the boot layer, where you have 2 roots, and it can update one and then boot from the other to provide atomic system updates, because the root that CoreOS is running on at any point in time is read-only. And then on top of that, they have systemd and etcd. Etcd is designed to provide configuration, communication, and locking between multiple instances. And then systemd is able to run services, and then CoreOS broadly supports using Docker inside those systemd services so that it's possible to basically say, here's an image, here's a fleet of machines, and it's called Fleet, actually the tool they have for managing sets of servers, run this somewhere for me. And it's smart enough to have kind of federation between those machines and communication about resources so that you're able to just treat a bunch of boxes, whether bare metal or big VMs, as just a pool of compute resources that you can launch these containers in on demand. And we've been, the systemd crew has been working together with Docker, and this is actually done by the CoreOS team of kind of creating this grid of standards of support for things where we want certain things to be included with every kind of container in order to harmonize the space a little bit more, because a couple of the ones that I didn't mention were OpenVZ, libvirtlxc, and those OpenVZ, I believe, still requires patches to the kernel. I don't think it's quite in the vanilla kernels yet, and that's one of the oldest containerization systems on Linux boxes. And then a lot of these things on the runtime support are actually systemd features for being able to introspect into the containers and realize that software is running in a container and configure various elements of that. To hopefully provide administrators with a more consistent experience so that these kind of pool of technologies, even if the implementation is different, the functionality is similar. And that's it. So I'll open the floor for questions and more discussion.